In this video, we'll be looking at optimizers. Those algorithms that we use to tweak gradient descent to make it work just that little bit better. Before we look at optimizers, we'll look at the perspective of stochastic gradient descent from a few theoretical perspectives to help us set up what we really need to make gradient descent work better. First, let's pick up on something we talked about in the last video, which is that the minimization objective that we use in deep learning is slightly ill-formulated, if we formulate it like this. If we take the loss of our training data and take that as the function that we want to minimize, then we end up with an optimization objective that we want to minimize, but we don't want to minimize too well. Because we know that if we minimize it absolutely, if we find the global minimum, that we actually find solutions that overfit. One solution to this problem is to phrase the minimization objective in terms of an expectation. So we see the data as being generated by a probability distribution. So that the data is now a random variable. And under that probability distribution, we take the expectation of the loss for the data. And the expectation, that's what we want to minimize. Now this is something that doesn't overfit because it's purely defined with respect to this probability distribution, and our test set comes from the same probability distribution. So whatever we learn in minimizing this particular objective will apply to the validation set as well, and the test set. In other words, this loss surface for the expected loss is one that doesn't have any bad minima. We want to find the lowest minima on this surface, and the overfitting, the minima that we're overfitting solutions are not minima in the expected loss. So this is a perfect situation, a loss surface that we can freely minimize on that will never overfit. The problem is that this is not a function we compute. This is not a can compute. This is not a function we have access to. Luckily, however, there are some results, most prominently the ROBBINS-MONRO algorithm, which tell us that if we have just an estimate of this function that we cannot compute, but we can estimate it, then we can apply gradient descent with the estimate of the gradient. So here on the left we see the gradient of the expectation of the loss, which is not a gradient we can compute, but we know that if we sample some data from this probability distribution and then compute the gradient of the loss for that sample, that's a good estimate for the gradient that we're actually interested in. And it turns out that with these estimated gradients, if we apply gradient descent, we can actually, under certain conditions, converge to the optimum almost certainly. Now these conditions are quite strict. It needs to be a convex loss surface, which of course is never true in deep learning, but we can think of deep learning as containing locally convex loss surfaces. So if we're within a neighborhood wherein the loss surface behaves convex, then within that neighborhood we will find the optimum. The estimator needs to be asymptotically unbiased, so the bias of the estimator needs to, we need to be able to make it as small as possible. And then the learning rate needs to decay in a very particular way. Now this is not something we usually do, but that's not really the point of this result. The point of this result is that based on samples from the data, we can actually find the optimum of this expected loss. And if we then deviate from these constraints that guarantee that we will do it, that's all right. So long as we know that in principle we can find it, if we tune our hyperparameters in the right way. Now you might ask, if this loss, if this minimum leads to guaranteed non-overfitting solutions, and we can find such minima by stochastic gradient descent, by sampling the data, why are we still overfitting? And that's because at some point the samples in our data will start repeating. We have finite data, and therefore we cannot take infinitely many samples with smaller and smaller bias. There is an irreducible bias to our estimate of the gradient which comes from the fact that we will eventually start seeing data points again and again and again. But up to the limit of our data, we can follow the Robbins-MONRO algorithm and make the bias smaller and smaller. And up to the limit of our data, stochastic gradient descent will move towards a global minimum. So now towards ways to improve stochastic gradient descent. You may ask, why do we need to improve stochastic gradient descent? What's wrong with it? Here's a picture to help explain that. Imagine that you're training two models, a convolutional neural network to consume images and a recurrent neural network to consume language. We haven't talked about recurrent neural networks yet, but for now, all we need to know is that these are very different models in very different domains, so it's only natural to expect that they require different learning rates. After all, the learning rate needs to be tuned. So far, so good. But then the question is, what happens if we want to combine the two? If we want to take a CNN and feed it its output to an RNN. For instance, to build an image captioning network, like we saw in the last lecture. A network that reads an image, captions it with a bit of natural language, and we want to train that model end to end. In that case, the two become one big neural network, but they still require these two very different learning rates. So what this tells us is that the more heterogeneous our neural network becomes, the more we need to tune the learning rate separately for every parameter. And that's something that stochastic gradient descent can't do for us. So to move towards models that can do, here's our plan. We'll start by looking into second order optimization, which is also known as Newton's method, which is not a method that is practically applicable for deep learning, but it'll tell us something and it'll give us a theoretical framework to sort of describe what we actually want to achieve. And then we'll look into the two most popular approaches to improving stochastic gradient descent, which are momentum and Adam. And then we'll look at, we'll have a quick look at some of the recent developments in optimizers this year and last year that it might be worth keeping an eye on. So we'll start with the gradient, which is what gradient descent is built on. And the gradient is defined as a linear approximation to the function that we are optimizing over. Specifically for one point on the function, it is the linear function that best approximates our function at that point. So the question is, if we want to improve on gradient descent, can we replace this linear approximation by a better nonlinear approximation? And of course we can. These are the so-called second order approximations. Let's look at how to find these. The first thing to do is to define this linear approximation properly. What we've done so far is find the gradient or find the derivative, but we haven't actually fully defined the function. For that we need to define both the slope, s, and the bias. Now the slope, that's the derivative, we know that already. And with this we can find the bias. And we do this by filling in a for x, which gives us this function. Now we know that at this point the approximation is exact, so we can replace fa by fa, and we can rearrange to give us this expression for b. If we then fill in b in the original function and rearrange a little, we get this expression for the linear function that best approximates f at the point a. And we will extend this principle to write down the best second order approximation. So this has the same sort of function as we saw before, the same sort of structure as we saw before. We have an approximation to f subscript a of x, which is a polynomial in x minus a. So we have c1 a constant, c2 a coefficient for x minus a, and c3 a coefficient for x minus a squared. And we want to find the constants that give us the best second order approximation. Now, to fill in these constants, first let's see what happens if x is equal to a. So this is the point at which we want to approximate. And note that the second two terms disappear because a minus a is 0. So if we set x equal to a, then we know that in order to approximate well, as good as possible, we need to set c1 equal to fa. And what we will do with these other two constants is we will use them to make the first and second derivative better approximations of our target function. So first we'll look at the first derivative of our function fa. The constant c1 disappears and we are left with c2 plus 2 times c3 xa. And if for this function we set x equal to a, the second term here disappears. And we note that we can make the first derivative of our approximation locally equal to the first derivative of f by replacing c2 with the first derivative of fa. And we can repeat that process. So we take the second derivative of fa, and the only term that remains is 2 times c3. And now if we set x equal to a, we note that this function should be equal to the second derivative of f at a. So c3 should be equal to 1/2 times the second derivative of f at a. So we fill in these values as constants, and we get our best second order approximation to the function at a. And depending on how much calculus you did, you may recognize this as the second order Taylor approximation of f. Now, how does this help us to better find the minimum of the function f? What we can do here that we couldn't do before is take this approximation and simply find its minimum. So we look at this parabola that we've now fit to the blue curve, and we simply figure out where the minimum of that parabola is. To do so, we take the derivative, which looks like this. We set the derivative equal to 0, and we rearrange. And one more step gives us that the derivative is 0 if x is equal to a minus the first derivative of f at a divided by the second derivative of f at a. So what does this tell us? Well, in a gradient descent setting, we can think of a as the point where we are now, the point where we are computing the approximation. In gradient descent, we computed a linear approximation for our current point. Now we've computed a second order approximation for our current point. So the current point is a. And the point where we want to go to, that point is x. So if we look at it like that, then we want to take our current point and we want to find a way to manipulate it in order to bring us to x. So that simply means from our current point, subtract this term here of f prime over f prime prime, and that will be our new point. So that gives us the following update. We've added a learning rate alpha here to make to help us scale the update, because this update is great if our second order approximation is perfectly correct. Then we can simply apply this update without any learning rate. But since we don't fully trust our second order approximation to be exactly equal to the function, we add this alpha, which takes the role of a learning rate, which tunes the extent to which we trust the approximation. And here we note that the update rule is very similar to gradient descent, except that here the gradient is divided by the second derivative. We can extend this to multiple dimensions, which is fairly straightforward to do, but we'll save you the work here. This is what you get. The update rule for our current parameter is the gradient of the parameters multiplied by the inverse of the Hessian matrix. So the second derivative now becomes a matrix. We're basically taking derivatives twice. So we can do that for every parameter the first time, and then for every parameter the second time. So we can arrange all those possibilities in a matrix that's called the Hessian. And that's the multidimensional analog of the second derivative. And the inverse of that Hessian plays the same role as dividing by the second derivative in the one-dimensional case. So this is what Newton's method looks like in higher dimensions. So is it practical for us in deep learning to use Newton's method? Well, if we look at the requirements, we need to build up an n by n matrix, where n is the number of parameters in our model. So if that's 1,000,000 parameters, then we're already looking at a matrix with 10 to the power of 12 elements, which is more than fits in most computer memory. Not only that, but we need to accurately estimate every element of that matrix, which requires very, very large batch sizes. Then we need an extra backward pass for each element of the gradient, because we're taking the derivative twice. So after our first backward pass is finished, we need to do another backward pass for each element of that gradient. And then if we finally have that matrix, we need to invert it. So basically, every one of these bullet points would make Newton's method a non-starter in deep learning, and all of them together makes it definitely a method that is not suitable for the kind of models that we're looking at. But what it does help us with is it helps us to understand and to analyze our problems. It basically gives us an ideal. We can see what would Newton's method do in this kind of situation, and then we can look at how we can approximate that with the means that we have. So let's look a little bit closer at what kind of problems Newton's method does solve. They basically come in two flavors. The first thing it gives us extra above and beyond the gradient descent is interactions between parameters. So note that if we do gradient descent, we take the partial derivatives. So we base our update rule on the derivative, which assumes that all the other parameters are constants. All the other parameters are not touched, but they aren't constants, they are touched, they will also be updated. If we update two parameters together, they can have interaction effects. And the off-diagonal elements of the Hessian give us all of these potential interaction effects. On the diagonal, we get information about whether or not we are nearing a local maximum. If you think back to the slide with the second order approximation, as we go near the minimum, we see that the second order approximation curves towards this minimum, and it tells us to start slowing down because a minimum is approaching. Here we see both options in one picture. We see that as we move from the starting point to the optimum, there's a slight curve in the ideal trajectory through which we should be moving. And this is what the off-diagonal elements of the Hessian can tell us, that as we add something to x, that will interact with y, and both of them should be taken together to give us a curve. And what we also see is an oscillation at the beginning, because the loss surface forms a kind of a gully, a channel, with steep walls. And the gradient for those steep walls is much stronger than the gradient in the direction that we actually want to be moving. So what gradient descent ends up doing is bouncing back and forth between these walls. And what the Hessian would tell us in this case is the curvature of this gully, which tells us that in the direction that we are now bouncing back and forth, we should actually be slowing down because there is a minimum nearby, at least a minimum in that direction. Now, if you imagine what the loss landscape of a purely quadratic function looks like, so that's a function that is perfectly approximated by this second order approximation, then you know that this function is a parabola, an n-dimensional parabola, and its isolines form ellipses. The lines of equal value form ellipses. So that looks like this. And what we also know for this kind of function is that the axes of these ellipses are the eigenvectors of the Hessian, are the eigenvectors of the matrix that forms the basis of this this function, which leads to a value called the conditioning number of the Hessian. And the conditioning number of the Hessian is essentially the ratio between the smallest and the largest eigenvalue of the Hessian. If you don't know what eigenvectors and eigenvalues are, you can simply think of the ratio between this larger arrow and this smaller arrow. And that simply tells us, for this particular function, how much it looks like a ravine. So the bigger the ratio is between these two arrows, the more poorly conditioned our Hessian is. And if the Hessian is poorly conditioned for a function that isn't a parabola, then we know that locally this is what the function looks like. If we have locally a poorly conditioned Hessian, we find ourselves in a ravine. So, if Newton's method doesn't help us solve these problems, how can we solve them? To summarize our requirements, the things that we can do for these large models, we require one backward pass. So ultimately we want to use only the gradient. Our memory use should be linear in the number of parameters that we have. So we can double the number of memory used, or triple or quadruple, but that's about it. And we only want to expend a linear number of computation, a linear amount of computation in the number of parameters that we have. And our first candidate for improving stochastic gradient descent is momentum. Momentum looks like this. Instead of applying the gradient directly to our current parameter vectors, we apply the gradient to a variable m, which is our momentum variable, and then we apply that momentum term as we did the gradient before. And this gamma value that we multiply by the momentum is usually something between 0.5 and 1. It needs to be smaller than 1, and it's usually larger than 0.5. What does this mean? How does this work, and why does it work? We'll look at three perspectives on how to arrive at these equations and how to understand what they do. We'll first look at momentum by a physical analogy. Then we'll look at the way it accelerates the gradients, and then we'll see that it computes an exponential moving average. So the heavy ball view of momentum is that the gradients shouldn't act like a direction in which we move directly, but like a force. So if you remember your physics, you know that a force doesn't act on the position of an object directly, it adds to its velocity. So if a force applies to a ball, then that force manipulates its velocity, and then that velocity manipulates its position. And that's what these two update functions simulate. Gradient acting as a force on our current value of the parameters. So if we think now as our current parameter value as a heavy marble rolling down the loss landscape, we can see that momentum can help it roll out of local minima. It can help it to dampen oscillations. If we remember, if we imagine a heavy ball rolling down this bowl in the middle, we see that it slowly comes to a rest. And it accelerates repeating directions. So in this 2D case at the bottom left, we see that if this starting point were a heavy marble, the sideways motion, the sideways oscillation would very quickly dampen out, and what would be left is a motion in the direction of the ravine. If all the gradients point in different directions, like in an oscillation, those tend to dampen out, and what's left is the gradient, what's left is the force pointing in the direction of the optimum. But what we'll see now is that if all gradients point in the same direction, if we get repeated gradients pointing in the same direction, that we end up actually accelerating the gradient descent, increasing the learning rate as we move along. We can see that by filling in previous values of the gradient descent. So if we start with a single gradient update like this, and we get another gradient pointing in the same direction, then the momentum term will look like this. And if we get another one after that, it'll look like this. And if we keep going like this, we see that if we take the d out of the sum, we end up with this infinite sum here in the limit of gamma to the power of n. And if you remember your infinite sums, you know that this infinite sum reduces to 1 over 1 minus gamma, which tells us that if we set, for instance, gamma to 0.99, then this value, 1 over 1 minus gamma, turns into a 100. So in the limit, we are accelerating the gradient descent by multiplying the learning rate by a factor of 100. If we're lucky enough to get a bunch of gradients all pointing in the same direction. Our final view of momentum is that of an exponential moving average. And to see why that might be useful, first note that averaging gradients helps to stabilize the progress of gradient descent. So what we see here is that kind of oscillation that's really harmful. Now, if we imagine in this oscillating regime, instead of taking these gradient steps, averaging a handful of gradient steps, and then taking a step in the direction of that average, we see that the oscillations will cancel out against each other, because there is many oscillations going to the left as to the right. So in the average, those will disappear, and what will be left over is a small gradient step in the direction of the ravine. And that's why averaging helps to dampen out these oscillations. And what we see is that momentum functions as a kind of average, specifically something called an exponential moving average. So we'll define what that is first, and then we'll show how it can be translated into momentum. So imagine you have a series of values, vectors or scalars. Then the exponential moving average is a value that you compute and update as these values come in, as these values are observed, one after the other. And the exponential moving average is defined as this. We have a parameter kappa, and the current exponential moving average is kappa times the current value that we're observing now, plus 1 minus kappa of the previous exponential moving average. So this is a linear interpolation between the value we are currently observing and the value and the previous value of the exponential moving average. So this is a recursive definition. And to see what it looks like for the whole sequence, we can simply unpack it one by one. So we can simply fill in the definition for the exponential moving average of n minus 1, which looks like this. And if we take the 1 minus k inside the brackets, we get this. And this pattern repeats. So as we extend the pattern, we see that every term has a multiplier k times 1 minus k to the power of how far back in history that term is. Now what we see here, if we set gamma equal to 1 minus kappa, and we take the kappas in the exponential moving average to the left-hand side, then we see that the exponential moving average divided by 1 minus gamma is equal to this momentum sequence that we are computing when we are doing momentum. So in short, this tells us that we can think of momentum as computing an exponential moving average over the gradients and then using the value of that exponential moving average in the gradient update. Note that the idea of taking averages in order to stabilize learning is not a new one. If we have, for instance, a mini batch of instances and we compute the loss over that mini batch by taking the average loss over the instances in the batch, then the derivative of that loss, the gradient of that loss, we can take it inside the sum, and we see that the loss for the mini batch is essentially an average of the losses for the separate instances. So if we are performing gradient descent on the mini batch, we are essentially doing per instance gradient descent, but averaging the gradients over the batch before doing the update step. So in this sense, we see that mini-batching also has this averaging effect and helps us to stabilize learning by canceling out gradients. So what do we pay for this benefit of momentum? If we have n weights, then we need n times more memory, because we have this extra value m that we need to keep in memory, which is exactly the same size as the weight factor. We need n extra operations, because we have one more summing operation, and we have one extra hyperparameter to tune, which is gamma. What we get in return is a potential quadratic speedup in convergence under the right conditions. We get per parameter tuning of behavior, because each parameter gets its own momentum. So we may expect a better response to heterogeneous neural networks. And there is much more to be said about what momentum really is and why it really works. And here's a good link to an article about that, but we won't go into it any further. Slight twist on momentum is Nesterov momentum. And the key to Nesterov is that you know that you are going to apply the momentum update when you already have it, and you know that you're going to compute the gradient. So if you apply the momentum update first and then compute the gradient, you can compute the gradient where you will be instead of where you are. So you do a kind of look ahead based on this momentum. That gives you a gradient, and then you apply the gradient to that. And in some cases, this can work a little bit better. Now, how can we improve on this even more? Remember from the first video, the conclusion we drew from the variances of the gradient norms. We saw there that if we had high variance, that we wanted to reduce the learning rate, because we noticed that the gradient descent was jumping over the important details of the loss surface, and that if we had low variance in our gradient norms, that we wanted to increase the learning rate to help it escape from local minima and move faster. So one computation that has this effect is the computation of normalization, which is what we do when we prepare data for processing it in machine learning. We compute the mean and the standard deviation, and then we subtract the mean to center the data around 0, and then we divide by the standard deviation in order to ensure that the data is properly scaled. And this has the same effect that we were looking at for the variance. If we have high variance, we end up with a lower value, and if we have low variance, we end up with a higher value. And this is the basic idea behind ADAM. Instead of exponential moving averaging, like momentum does, we do exponential moving normalization. So we compute an exponential moving average, which is our mean, and then we compute another exponential moving average for the second moment of our distribution. So this isn't quite the variance because it's not centered. We don't subtract the mean before we square, but basically it is still an estimate, an exponential moving estimate of the second moment of our distribution on the gradients. And note that we're doing a proper exponential moving average here. So we have these two parameters, b1 and b2, and the current estimate of the mean, for instance, is b1 times the last estimate of our mean, plus 1 minus b1 times the most recently observed value. And the same for the estimate of the second moment. And these two terms we can then use in an update to give us a normalized estimate of the current gradient, and that we subtract in place of the normal gradient in gradient descent. And that's the basic idea behind ADAM. We divide by this estimate of the second moment in order to control for variance. If we initialize our m and v to 0, then we create a little bias. So the proper implementation of ADAM includes these bias correction steps. Note that at the start of learning, these are substantial, but as learning increases and this value t increases, this correction fades away essentially, because b to the power of t and b2 to the power of t both vanish to 0. So with Adam we pay 2n extra memory because we need to store an m vector and a v vector, and 2n operations because we have these 2 exponential moving average operations. We also have 2 extra hyperparameters to tune, b1 and b2, beta 1 and beta 2. But especially with Adam, the defaults are usually fine. So there are good defaults for beta 1 and beta 2 given in the paper, and practically you almost never have to change these. And as a result, the learning rate becomes much easier to tune. So even though we now have 3 hyperparameters, practically there is usually less hyperparameter tuning to do. Adam doesn't have any convergence guarantees. It does give you per parameter tuning of behavior, a real per parameter learning rate basically, and it's currently the default optimizer for most deep learning settings. So let's look back at what we've seen. We've looked at Newton's method. We know that it doesn't work for deep learning, but it is good in other settings, and it gives us a theoretical framework to analyze optimization in deep learning. Practically, if you're doing deep learning, our advice is to start with Adam and try learning rates between these reasonable values. Keep the defaults for beta 1 and beta 2. And consider trying also plain SGD with Nesterov momentum if Adam doesn't work for you. So to finish up, let's look at 3 developments from the last 2 years in the area of optimizers. The first that we'll look at is rectified Adam. Rectified Adam is born out of the observation that a lot of people found that in using Adam, they required a learning rate warm-up. So the conclusion is that Adam must in some way underestimate the variance observed in the early training and not properly correct for that. And this is experimentally showed in these joy plots here. So what the authors of Rectified Adam, or R-Adam, came up with was a rectification of the variance estimate for Adam. It looks like this. We won't go into why, but it turns out that this works a lot better, especially if you are training transformer models. Another new development is LOOKAHEAD. LOOKAHEAD can be used by in combination with any optimizer. We train 2 models, W and V. We train W normally by any optimizer, could be Adam, could be SGD. We let it run from the starting point for a while, and after a while we say stop, and then we push V towards where W has ended up. And from that point, again, we let W run along a little bit under the influence of its basic optimizer, and after a while, we take that as a look-ahead point and we move a certain distance toward that point, and so on, and so on. And you can think of this as kind of the idea of Nesterov applied to gradient accumulation. Finally, another optimizer that is gaining in popularity, the LAM optimizer, which is based on the older Lars optimizer from 2017. And the idea of Lars was to tune the learning rate not per weight, but per layer. So we look at the weights of layer L, and we compute this ratio here, the norm of the weights over the norm of the gradients. And that tells us something about how much the weights are likely to change in relation to the gradients. And we can think of that as a confidence or a trust in this layer that we can use to tune the learning rate. And LAM then applies this principle of Lars but instead of combining it with SGD, combines it with the Atom update, together with some other tweaks. So that's all for optimizers. In the final video of this lecture, we will look at a large collection of tricks and techniques that you need to know in order to train large neural networks effectively.